Hello and welcome. Here's a question to ponder. What's the speed of time? 1 second per second? Thankfully, we don't have to answer that question today. In this video, we're going to look at how to use derivatives and tangent lines to approximate the values of functions. This is a process called linear approximation. So let's look at the notes for some details. So as it mentions, we can approximate functions with tangent lines when we're close to the point of tangency. And the picture off to the right shows that. Here we have the graph of x squared, and then we have a tangent line to that graph at x equals 1. Now as you're close to that point of tangency at x equals 1, the y values of the tangent line and the y values of the x squared function are really close to each other in value. They're almost exactly on top of each other. Now as you stray farther from the point of tangency, then the y values of the tangent line and the y values of the function x squared start to drift apart from each other. They start to be different. But at least as long as you're close to that point of tangency, the y values of the line, the tangent line, and the y values of the original graph are pretty close to each other in value. So we can use the line to approximate the function as long as we're close to x equals 1 in this picture, or to the point of tangency in general. And since linear functions are relatively easier to work with, like that line equation of 2x minus 1 can be easier to work with than any arbitrary function. X squared is not too bad to work with, but you can imagine some complicated looking functions. This can really help simplify calculations. And sometimes if you're taking a physics class, you'll notice it. Like all of a sudden, sine theta will be replaced by theta in some pendulum equation. And you wonder, well, what's going on there? And that's because of the tangent line of sine theta at theta equals 0 is just theta. That's the equation for the tangent lines, y equals theta. So they're replacing sine theta with theta, which is like replacing the a more complicated function with a simpler function, a linear function, y equals theta. It just helps to simplify the calculations. So suppose we want to find the tangent line at x equals a in general. Then we have this point a comma f of a on the line, and the slope of the tangent line is going to be gotten by the derivative. The derivative is the slope of the tangent line. So that would be f prime of a. So using point slope form, we would get y minus f of a equals f prime of a times x minus a. This is nothing new. Back in other previous packets, whenever we ask for the equation for the tangent line, that's exactly what we do. We find a point on the tangent line, we find the slope of the tangent line using the derivative, and we put them together using point slope form to get the equation of the tangent line. Here it's just written in general for x equals a and some function f of x. Now we could rewrite that equation using function notation by adding the f of a to the right, and instead of y we could write capital L of x, for example. L standing for the linearization. The linearization of f at a. So this is just taking the function and turning it into a line, basically, at that particular x value. So the note is that when x is close to a, the function values are approximately the same as the line values, as the tangent line values. Again, we can just look at the picture right here. In this example, the function values of x squared are very close to the y values of the line, 2x minus 1. They're just very close to each other as long as x is close to the point of tangency, which in this case is 1, so like a would be 1 in this picture. So let's look at example 1, which says find the linearization, in other words, find a function version of the tangent line of f of x equals the square root of x at x equals 4. The picture is off to the right, so here's the square root of x. Here's x equals 4. So we're looking for the equation of this line, this red line, L of x. Well, using that kind of formula, you could call it, that we came up with just a moment ago. Really, it's just point slope form, but solved for y. We need to find f of a and f prime of a, where a in this case is a is 4. Well, f of a, in other words f of 4, is just the square root of 4, which is 2. So that's not too bad. F prime of a, well, we need to get f prime of x in general before we can get f prime of a, so f prime of 4. And to do that, we take the derivative of the square root of x. Here I'm going to write the result. You end up getting 1 over 2 times the square root of x. Remember that to take this derivative, you can write the square root of x as x to the 1/2. Then use the power rule. And then simplify. The negative power on the top, negative power, will bring that particular factor to the bottom of the fraction as an x to the positive 1/2, which is the same thing as the square root of x. So now we can take x equals a, so 4, and plug it in to get f prime of 4. So here we get 1/4. So then, to get the linearization of the function, in other words, the tangent line written in function notation, we're going to take f of 4 plus f prime of 4 times x minus 4, right? We're just writing down f of a plus f prime of a times x minus a, where a is equal to 4. F of 4 we found to be 2. F prime of 4 we found to be 1/4. And if we simplify this a little bit, the 1/4 can distribute, and we'll get x minus 1. The 2 minus the 1 gives us 1. So we have 1/4 x plus 1. So that's the linearization of the square root of x at x equals 4. In other words, it's the equation of this red line in the picture. Notice that the slope is 1/4. Rise over run from this point to this point is positive 1 in the y direction, positive 4 in the x direction, so the picture matches the slope there. And the y-intercept is 1 in the picture, which is exactly what we got. So we got the equation for that tangent line at x equals 4. Now we said that the y values of the tangent line, of the linearization, which again is just another word for the tangent line written in function notation, the y values of that tangent line are the same, or almost the same, as the y values of the function square root of x, as long as you stay close to x equals 4, right? They're right on top of each other, right on top of each other. So this can help you evaluate things like if you wanted to know the square root of 4 plus 2, well, that's approximately equal to, so that's like, taking x equals 4.2 and plugging it into this square root of x function. But we said that the square root of x function can be approximated by 1/4 x plus 1. So instead of plugging in 4.2 into the square root function, we can just plug it into the linearization. We can plug it into 1/4 x plus 1. And that's a much simpler calculation. That one you just take 4.2 divided by 4, add 1. You could do that one by hand and you'll get 2.05. Much easier to get that result than it would be to get the square root of 4.2, just in terms of calculations. And notice that linearization, that value that we got by using the line, linearization, is really close to the true value of the square root of 4.2, at least out to this many decimal places. The error between these two is very small. It's 0.0006 approximately. So as long as you stay close to the point of tangency, which was x equals 4 in our case, the line, the tangent line, approximates the function values very well. Let's get even closer to the point of tangency. If you plug in 4.05 and use the tangent line for that instead, notice that the difference between the approximated y value or output and the true value are very, very small, even smaller than before as you get close to the point of tangency. 4.005, even closer. The error between the approximation and the true value is even less. So that's it for linearization. In the next video, we're going to look at differentials, which are, instead of getting an equation of the tangent line, we're going to take a walk along the tangent line. So thanks for watching, and see you in the next video.